and angular components. Okay, so in 1 mark or certain questions like that, you can expect what are the radial and angular part question, or only for that expression you need to mention. Or if it is multiple choice, they give you 4 options with one right answer, so you need to pick that up. Okay? So these are some basics in last class what we have discussed about subatomic particles. Now let's start to assemble them, like few electrons bring closer together because they are attracted by nucleus, and make it more and more building up. Okay, with this introduction, I just want to ask, probably whoever is aware, they can answer. What are the bonding theories you are aware of, and what are the failures in bonding theories which led to the development of molecular orbital theory? Anyone in the class, you may tell your name and then you can start answering that. Yeah. Anyone in the class who would like to give some, as I told you, you need not tell exact definition and all. You can say very vaguely the bonding theories and what made it to go for more and more like molecular orbital theory. Anyone in the class? I don't think so. It is very, very hard because you must have studied from your school time. Yes. What are the various bonding theories what you are aware of, and what made it to go through molecular orbital theory? Yeah. Anyone?
Valence bond theory.
Okay, valence bond theory. Yeah. Any like I mean, for example, what made people to go directly to valence bond theory?
Westphal theory.
Yes, VSEPR theory. Yes, valence shell electron pair repulsion theory. Yes, I'm asking how from valence bond people went to like Despard theory, like that. For what reasons? And you can tell any 1 or 2 reasons.
To identify the valence electron in outermost shell cell.
Okay, to identify the outermost electrons in the valence shell, and how stable they can form to avoid repulsion and all those things.
Okay. To get the octet configuration.
Yeah, octet was started earlier, much before. That was probably like first or few bonding theories. Later, valence electrons are only responsible for bonding, like either sharing, transfer, all those things. Later, it has slowly developed with the failures. Yeah. Okay. I think few of you could raise, but since the question itself is a very broad topic, and I don't expect like straight away, for example, exact loopholes in these things. Now, let's see what we can understand from molecular orbital theory. Still, I see only like there are only 42 students. Okay, so I want everyone to join. Please make it a note. Okay, you join all like 56, whatever is your class 10, unless there is some issue with your internet or whatever. Yeah? So all of you please join before 1:20 next class onwards, or whenever we have this. Okay, let's go to the topic. This is what we are going to discuss today about just a minute. Just a minute. I think there is some issue in the. Yeah. Okay. So you can see the slide right now. Yes. I hope we can see the second slide right now.
Yes, sir.
Okay, so these are the various bonding theories, and many of you are familiar. Even if you are not familiar, just try to recap what are the bonding theories it is required. And again, do keep in mind we are talking about electrons, electron density, probability of finding electron. Okay, no octet. No, it's not like complete electrons, not even valence electrons. Okay, we are still in the electron probability of finding an electron in certain space. With that background, we are coming to molecular orbital theory. But before starting molecular orbital theory, everyone should be aware of these basic theories like valence bond theory, Lewis bond theory, and so on. There are a lot of developments in the bonding theories. However, this is what I was asking all of you. What made it to look for even that VSEP theory at the same time, valence bond, all those things, even though, like, as I think some of you pointed out, that octet rule is not really followed for, like, electron deficient compounds, okay, like boron based or like nitric oxide. Octet, like, exceptions were there. And also the bonding theories, whatever Lewis and things were developed, were not really applicable for transition metal complexes. And very important aspect is why liquid oxygen is attracted towards magnet. You may be wondering how oxygen, I think now you understand the importance of oxygen. I mean, you're all aware that it is essential for life, breathing and all those. And also due to this COVID things, the surge of oxygen is also becoming more and more, like, people are really looking forward for like oxygen gas for their breathing and other issues. So one important point you should consider in any of the theories which fail to explain oxygen's magnetic nature, okay, which we will try to look into molecular orbital theory. Okay. To just recap the basic theories and also to start class in a more funnier note. Probably you might have seen some various several cartoons. So covalent bond is like, for example, sharing between those two atoms, and like metallic bond, you have like a pool of like, electrons going around the nucleus. And in the case of ionic bond, you see a transfer of one species upon the, and also for various coordinate type of bonds, there is a coordination between two atoms. Okay, so this is just to start a simpler or a easier way of looking at how transfer, sharing, or coordination between two atoms or two systems happen. Now, let's understand more deeper how the bonding takes place. So you're aware that when two atoms approach each other, we start seeing a bond. Okay? So now let's construct hydrogen molecule from hydrogen atoms. Okay, it's very simple. Two hydrogens, when they come close together, you get hydrogen molecule, which is a covalent bond. I think it's very straightforward. We can write H, H2. But in reality, please try to look at more deeper based on this graph. So this is the graph between internuclear distance, means two nucleus when they are approaching together, two hydrogen atom nucleus. What is the minimum distance? That is the bond length where hydrogen can interact, and energy required to bring close these things, or what is the minimum distance they can come and they form a bond. Why don't it happens if you press it more? I mean, if the more hydrogen with the bond length decreases, what happens? Now, so everyone try to understand this. We were discussing in the last class that electron means you can't just write one electron here. Okay. Now you need to mention it as probability of finding the electron in electron density. So you tell that at some certain point of time, electron will be located in this space. So this is hydrogen atom, one proton, and probably nucleus and electron density, and nucleus electron density. So two hydrogen atoms are coming together. Okay. Once they start, they are very far away now, these two things at infinite distance, let's say. So there is no interaction. Once they start coming nearer by. Okay, then both of them start moving. What happens? There is a electron density overlap or slight electron repulsions. Okay, and atoms from, for example, electron density here will try to interact with the nucleus of one atom and vice versa. So you see such interactions when they are coming closer. Okay, at one particular time, where it is called the bond length. Okay, between hydrogen. Once they form, it is difficult. Electron density still moving closer towards the nucleus. Okay, because you already have electron repulsion or electron density repulsion. Okay? The same thing has been depicted in a graph or a plot. So this is the distance when the two hydrogen atoms are apart at infinite distance. You see the energy is close to zero. Okay, no energy like between them, they are zero energy. Once they start coming closer, okay, you see that the energy value varies. Okay, and they are at almost a certain distance where it is not a covalent bond between them, but there is an influence of one electron density with other electron density, which is felt. Okay, nucleus with electron density like that. Once it starts to feel, you can see there is a change in energy. And then finally what happens at 0.074 nanometer. Okay, almost like 0.74 angstroms where the bond length of hydrogen happens. That time we almost have energy of minus 458 kilojoule per mole. Okay, again minus that enthalpy and entropy, I guess probably basic understanding we'll have. We'll discuss more about that in the thermodynamics chapter, but essentially you want to understand there is an energy bond formation happens. Two hydrogen atoms, when they are coming interacting together, you see a covalent kind of bonding is formed with the dissipation of energy of minus 448 kilojoule per mole. And you can see here there is an optimal distance. Again, when you try to push them, okay, what happens? Electron repulsion, nucleus repulsion. So it takes infinite amount of energy where you both the hydrogen atoms cannot be crushed together. Okay, so that is what it requires, infinite amount of energy. While other things you need to have until bond length formed, you have an optimal energy considerations. So like this, two hydrogen atoms will react to form hydrogen molecule. Okay, so it is very easy to mention H giving rise to H2. But look at, after knowing Schrodinger equation, after knowing Heisenberg principle, you are no longer calling it as electron density overlap. Okay, electron density overlap, and then you get a bond length. Okay, where this bond length is the lowest energy from considering from this bond length form as compared to even if you bring them closer. Now, this is what happens when they are sufficiently apart, no interactions. Once they are together, you have lowest energy with the two nucleus like forming between optimum distance and called as bond length. Now, same thing, we are now no longer looking as electron, as I told you. You are looking at how electron density plot. Okay, so this you might be wondering how we get. Are we drawing it or how we get? So this, what happens, you start calculating from various computational models. Okay, and this is not done right now. It has been done like at least some 10 to 15 years back, where there is a lot, or even more, when the multi-orbital theory were developed. Okay. Now you see that you are no longer writing plus and one minus, plus and minus. You are writing it as electron density, and you see that there is here the probability of finding the electron is more, and as compared to here the probability. So we write some distributions. Okay, so how electron density is placed between two hydrogen atoms. Okay, this is for hydrogen molecule, the electron density. Now, Since already we started the class with VSEPR theory and what are the bonding theories, what you learned, let us know the failures or how those a quick recap happens, okay, between all these theories. So we now know when two atoms come closer, they form a bond. Now, are there any issues? It's not only hydrogen, right? We have like multi-electron systems. So what happens in that case? If we have like valence shell electron pair repulsion theory, where it is used to figure out some geometries of molecules, especially like non-metallic ones. So now the main postulate is the structure of around a given atom is basically understood by minimizing electron pair repulsion. That is what it is, VSEPR theory. So you have minimum electron repulsion. That is the reason you can form bond. Again, it is optimal bond length. Okay. Again, now for hydrogen only we are seeing this case. But if you have non-bonding or lone pair of electrons, imagine the situation. There you will have again electron-electron repulsion more. So even those aspects are also considered, based on which we deviate the structures of water molecule and ammonia molecule as compared to sp3 hybridization and so on because of lone pairs. Okay, so I guess depending on the electron pairs, we can form a linear molecule, okay, or a planar molecule or a tetrahedral. In tetrahedral, the special case can be water ammonia, where we can have V-shaped or, for example, planar kind of, or like more like distorted tetrahedral kind of configurations, or trigonal bipyramidal if you have 5 electron pairs, and an octahedral 6 electron pairs. Okay. So I'm pretty sure that entire class is aware of how to draw them and with what overlaps they form. So let us not go more into details, but you should be aware that there were some failures with this, which made MO theory more appropriate for upcoming chemistry or upcoming structures. Okay. If you go to some of these like all these videos or like websites, you may figure out there are several models created by which you can really understand the structures, yeah, of linear, tetrahedral, and V-shaped molecules, and so on. Now, till now, as I told you, from your mind, we need to remove that electron, one electron, put a nucleus here and electron here. We should remove from our mind that, and we need to talk more about probability density. Okay. If someone says there is the location of electron, so you can say somewhere the electron density is in this region. So we can definitely figure out electron positioned at this particular place or like that. Okay, not at exact point, but it is placed in this particular region, which is why it is called probability density. So, which means you are finding an electron at a particular point in space. Okay, and you are already aware that from Max Born approximation, it is square of wave function. Okay, instead of psi, we call psi square, which will give you more probability. Okay. So instead of a very concentric thing, we have a diffuse kind of, like, more like models. Earlier we can say nucleus, one electron is revolving around this, but now it's a diffuse electron at this particular place. It can be placed here or it can be moved x plus delta x. All those points we'll be able to tell from this all this Schrodinger equation, Heisenberg, and so on. Okay. So this is where even in the last class we have discussed orange color represents a positive, for example, a sign, positive like the wave function, and blue one represent like negative wave function, and so on. Okay. So here in between you cannot find the electron either here or here. Okay, so these are the things. Basically, we gave wave function. Wave function can be positive or negative, but the square of it will always be positive. Okay, which is what is called as Max Born approximation, and also the probability of finding subatomic particle is absolute in that case. Yeah. With all this background, let's come to what is molecular orbital theory. In molecular orbital theory, we start emphasizing more often on probability density, or we talk about waves, constructive interference, destructive interference. Okay? So it is essentially the quantum mechanics extension, but again talking about probability densities. Okay. So even though valence bond theory or VSEPR theory does a reasonable job, okay, compared to octet rule, which is a very first model, compared to that, this valence bond theory, after bringing the hybridization, it gives very important, it does a very good job still, okay, especially for simple molecules. And so what it is generally being considered as a first approximation. First, you should know what is the structure or what is the hybridization and how far you can put the electrons away, okay, valence electrons. But this valence bond theory and subsequent theories, they failed to even describe simple molecules like oxygen. Okay, and also the same valence bond theory cannot be applied for complex polyatomic molecules, including transition metal complexes and so on. Okay, so this molecular orbital theory, it is essentially based on quantum mechanical model. Okay, as I told you, this diffuse, all those things, which you can apply for both simple molecules as well as complex polyatomic molecules, including transition metal complexes. Now, everyone, as I told you, should understand no longer electron and this one. You need to understand atomic orbitals. Even this is same in the case of valence bond theory and so on. So here, in the case of atomic orbitals, like for example, it is like two atoms together. So in atomic orbitals, these are the regions in space where you have a high chance of probability of finding an electron. Again, electron is not one electron, it is the electron density, which is like spread out, okay, in that particular atom. So it is atomic orbital. In that spherical orbital or dumbbell shape orbital, you can easily say electron is placed in this spherical thing, or a dumbbell shaped p orbital or double dumbbell, whatever, all those. So these molecular orbitals, if you combine two atoms, we get a molecule. Same way, if you mix two atomic orbitals, we start getting molecular orbitals. So it's a simple translation. Okay? It's an extension of this atom to molecule, atomic orbitals to molecular orbitals, which spreads over all the atoms in a molecule. So again, we should make sure that the electron density is residing within the molecule. That is a very important point, which you should be also considering. So what we discuss in our next classes and so on is, MO theory fairly explains qualitative, at the same time quantitative considerations of atomic orbitals to molecular orbitals. Okay, so it says a lot of implications regarding bond order, bond length, and so on. Okay, so very important aspect why you want to learn all this is using this MO theories, you can predict the structure, and which will, okay, if I predict the structure, like how it will be helpful. From various spectroscopic techniques, whatever structure you have predicted, it will be resemble. Okay, it will be resembling to that of whatever has been observed. Whereas other theories, what happens, there is some mismatch, a significant mismatch, or sometimes if it is totally wrong. But with this, you have a more overlap or high significant amount of overlap with various spectroscopic techniques, which is why LMO theories is very important, and it's an advanced version of various bonding theories. With this introduction, let's look at what are the significant attributes of molecular orbital theory. So essentially, it tells you the distribution and energy of electrons in molecules. Okay, so it talks about electron distribution, or what is the energy, lowest energy or highest energy, and very important, looking at the properties. Okay, stability of the compounds also can be analyzed. Okay, when I say compounds, it means molecules, like polyatomic molecules, or from simple atoms to it can be like diatomic or multiatomic molecules. And if you know that molecule, even when it is in the compound form, you can also say that kind of property. For example, optical property, okay, or it can be called even like magnetic property. All these things can be helpful. Very important aspect to know bond energy. Easily, by looking at some molecules, you can say whether it has got strong bond energy, or to dissociate them you require more energy, or it requires very small amount of energy to separate them. Okay, and also very important aspect is electron cloud distribution. Okay, so now no longer electron distribution, electron cloud, since it is a probability of finding electrons, so you call it as cloud. And magnetic aspects of some molecules also will be discussed in coming classes. So let's, in today's class, we shall discuss some important postulates. Later, if someone has any clarifications, we can discuss that. Now, what are the important aspects of molecular orbital theory? First thing is atomic orbitals. When two atomic orbitals they combine, you start getting molecular orbitals. And molecular orbitals, they have different energies depending on what is the overlap. Okay, I hope this also many of you might already learned, but still to make it very clear, when two atomic orbitals, when they approach, you can have bonding orbitals, okay, which energy will be lower than atomic orbitals. Non-bonding orbitals, same energy as compared to atomic orbitals, and anti-bonding orbitals. Okay, let's not directly discuss the terms now. In anti-bonding orbitals, you have higher energy than corresponding atomic orbitals. Okay? So it's very straightforward case. You bring two atoms together, you see whether they interact, or once they interact, what happens? Obviously the energy should be lower than the two atomic orbitals. Same way, instead of calling it as a molecule, we call bonding orbitals, and non-reacting non-bonding orbitals, which are, for example, anti-bonding. Okay. So where they are really placed at higher energies. Now, looking at all this, as I told you, we need to consider atomic orbitals overlap as like waves being overlapped. For example, if you add two waves or subtract two waves, what happens? Same way, let's look at how the molecular orbitals are formed. Now, if you, as I told you, electron cloud in atomic orbitals can be solved by waves or Schrodinger equation. Also, for example, wave function psi. Now, you already have seen in last classes, like in any s orbital, p orbital, or like that, you have a node. Okay, where you cannot find the electron at that particular place, zero at some particular places. So the waves will have, means the psi, for example, psi wave function can have positive phase or negative phase. Okay? So it can be plus or minus. So now easiest thing is plus plus, how what happens? or minus minus, if they interact, what happens, and plus and minus. If you understand that, that's all is entirely about molecular orbital theory. But there are few exceptions which we need to know it more. So now, whenever you start molecular orbitals which are formed from atomic orbitals, there should be a combination or mixing up of two wave functions. Okay, so how these these two wave functions they combine to form molecular orbital. Yeah? This is the main thing. I don't know. There is some chat. Someone say during attendance. Yeah. Okay, Verma. Just wait. Yeah, I'll tell you attendance. Don't tell. Right. Okay. So how these phases, when they combine, and they can also determine the shape of that molecular orbital. Yeah, these are very important considerations which determines how the molecular orbitals are formed. With this introduction, I will just today probably show you, and tomorrow we can discuss about how the addition happens. Now, I think in your last class or last semester, you must have studied about interference. When two waves overlap with the same amplitude, frequency, when they are traveling in same direction, when they interfere in phase, you call it as constructive interference. Out of phase, it is destructive interference. So what happens here is, you have two waves with the same amplitude, frequency, and wavelength. They are traveling in X direction or Y direction or Z, whatever direction it is traveling. What happens when they react in phase? So these are the two waves. For example, you can see now this wave and this wave, when they combine, you get constructive interference. When this wave and this wave, when they interact, you will be getting destructive interference. Right? I think this is very straightforward. So now our molecular orbital theory is based on such principle. Okay, so how these things they travel, and what happens to the amplitude and frequency, all those aspects will be considered when they are traveling in the same direction. Okay, so whenever you call constructive interference, when both the waves are in phase, for example, these two, you get constructive. When out of phase, plus and minus, you start getting destructive interference. So now wave function can be in phase or out of phase. Okay, psi A plus or psi A minus, what happens? Yeah, that is what we are going to discuss. So now we no longer talk about electron transfer or sharing, all those things. One electron, no, we no longer talk like that. We talk about electron density is being, for example, we talk about wave function, okay, electron density, probability, all those things we'll be talking about. Yeah? So with this, probably I think we can today end the class in 1 or 2 minutes. So in molecular orbital theory, we talk about how individual atoms, they produce like molecular orbitals from atomic orbitals, not atoms giving to molecules, atomic orbitals, like for example, s orbital, p orbital, when they react, what happens? Okay, whether we get lowest energy, which is obvious, but how it happens when the electron density, all those things, we should be removing from our mind till now, whatever we have learned about basics of bonding theory, a localized bond we should remove so that we have spatial idea, spatial overlap should be more considered. Yeah? So with this background, I think today we can stop. In tomorrow's class, we will discuss more about how the molecular orbitals are formed, and we'll take few examples, and then we'll try to calculate bond orders, and also we'll see what happens if we add more charge, okay, or how in what way bond order and energy, bond energy are associated. All those topics we'll be discussing in tomorrow's class. Yeah? So now I will do anyone have any doubts now? Does anyone have any doubts? Any particular topic or today's thing, you have any doubt? Since we are taking attendance, I think we can stop the recording. Yeah.